Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So we continue with our discussion of class 12 physics. So now we've made a lot of progress in terms of the electricity and magnetism. We're going to kind of stop working with that right now, and then we are going to little bit go over, what is, modern physics. But before I end the discussion on electricity and magnetism, I'm going to kind of look at one last topic. Okay, we already looked at electromagnetics, right? So now this is unfinished business, so that's why, and we are already discussing the class 11 material as well, light, right? We are looking at optics, right? We are looking at yesterday we looked at reflection optics, right? So we looked at refraction optics and now related concept with respect to light is the polarization of light, which we discussed actually in the context of class 12. Okay, so light, as you know, is an electromagnetic field. We discussed this last class as the last element of um, of light, right? And we said that it is an, when we say it is an electric and a magnetic field, we said that basically both the electric field and the magnetic field share a common wavelength, and the electric field is perpendicular to the magnetic field, right? And the direction of propagation is in the direction of E cross B, right? Where E is the electric field and B is the magnetic field, right? So E cross B will give you the direction of the propagation of the wave. So if E is along X and B is along Y, then the wave is going to propagate along Z, and as a result, we said that light is also a transverse wave. Okay, so the direction of the electric field and the direction of the magnetic field, right, are perpendicular, right? And so light is this is the wave understanding of light. Okay, there is also the idea of the photon, right? The photon is the particle understanding of light, right? We have electron, which is also, both a wave and a particle, right? So we will come to that side of things as we go into the next set of discussions that we have in modern physics. Okay, but before that, let's close down light as a wave. Okay, so polarization refers to the direction of oscillation of the electric field. Okay, so now you see that this light has a wavelength, right, and a frequency, and the product of the wavelength and the frequency is equal to c, which is the speed of light, 3 into 10 to the power of 8 meters per second. It is, as all of you know, light travels incredibly fast, and it is defines the highest speed at which anything can go, right? And therefore we said the speed of a wave is omega by k, right? And k is 2 pi by lambda, right? And omega is 2 pi f, right? 2 pi f by 2 divided by 2 pi by lambda will give you omega is 2 pi f, omega by k is the speed, right? C equals omega by k, 2 pi f divided by 2 pi by lambda. So the 2 pi's cancel, and you have just merely frequency times the wavelength. C equals frequency times the wavelength, right? For the wave, right? So you have E naught equals E equals E naught sine kx minus omega t, right? With respect to the wave, right? And we discussed the x, y, and z, the direction of propagation of light, right? We discussed all this in the previous class. Linearly polarized wave. State of polarization is the projection of locus of an electric field on a plane perpendicular to the direction of propagation. Okay, so now we say that light is plane polarized. The two words come together, plane polarized. What does that mean? It's plane polarized. That means that the E is confined to a certain plane. Okay, the E is, see, the E could be going like that, but plane polarized light, we say in the below picture, we represent a plane polarized wave confined to the XZ plane. Okay, so it stays in that one plane. It does not like rotate and occupy more planes. It stays within that one plane. It's a sine wave within that one plane. Okay, so we say that that is a plane polarized light. Okay. Now, an unpolarized beam, on the other hand, will have a large number of component waves, various different waves of different wavelengths and different polarizations. Okay, we say that randomly polarized light, combination of component waves of varying frequencies, varying waves, just coming out of a beam of light from a battery or a torch, right? Light from a torch or a bulb, or even the light from the sun is, polarized in many different ways. Okay, so now, so that is said to be unpolarized light. Now, if you have polarized light, you will follow this rule: plane polarized, or it will follow a certain system where the electric field is in this direction, the magnetic field is in this direction, and the plane proceeds in that direction. Now, how to obtain polarized light? An unpolarized light is polarized, that is, right? Randomly oscillating electric field can be confined. You take unpolarized light and you confine the electric field to be in one plane. And that is done by this thing called a polarizer. Okay. Now, the simplest and most widely used is a sheet polarizer, or what is called a Polaroid sheet. You might have all heard about this Polaroid camera, right? Polaroid camera typically has a Polaroid sheet. Okay, so and that is the primary way, by using a sheet which polarizes the light. Now, the Polaroid, right? It comprises of a long chain of polymeric molecules which are almost aligned like a wire grid. Okay, so now when you pass through, it'll let only one set of light pass through. So that is a Polaroid sheet. Plain polarized light, on this side of the sheet, you have unpolarized light. On the other side, you have plain polarized light, which is confined to certain plane. Okay, there is no change in intensity if we rotate the polarizer. Okay, polarization parallel to long chain suffers loss. Okay, and the horizontal is known as the pass axis. So there is one axis which is led through, the other axes are all shut out. Okay, so as a result, you have to use a very high intensity light, at least in the direction of the polarization. Okay, and then you can cut out the other, filter out the other one. Okay, so that is with respect to polarization. Okay, so that was the last piece of information that we wanted to share with you with respect to polarization. So now we are now going to go into a little bit of modern physics. Okay, so now first we are going to discuss. There are many parts of modern physics. Okay, so first we are going to discuss what you will also learn in chemistry, which deals with the atom. Okay, now how was the discovery of the atom, the model of the atom, the electromagnetics of the atom, right? All these will come into play. Then the second part of it will deal with the nucleus and the nuclear forces. The third part of it will deal, once we've looked at the atom, we've looked at the parts of the atom, which will deal with what are called, which will take a step back into your what you learned in electromagnetic theory, right, with electric circuits, right? So now we'll take a step back and introduce these electronic devices. Okay, so we will learn about conductors and insulators. We already learned about conductors and insulators when we studied electromagnetics. Now we will introduce this new thing called a semiconductor. So, but before that, we first have to introduce the other parts of modern physics, which include atoms. So let me give you a quick rundown of these two things. Okay, so let me do that quick rundown so you kind of know what's to come. Okay, so the first thing that's to come is deals with atoms. Okay, so we will discuss the various atomic models. Okay, and we'll take several lectures to discuss these. Okay, so Thomson model, Rutherford model, and finally the Bohr model. Okay, and so my aim is not to bore you. This is very interesting material. You will not be bored. Okay, it builds on the material you already learned, and we will touch upon the ideas that made up what is called quantum theory. Okay, what is this quantum theory? Quantum theory states that energy happens to be in levels inside an atom. Okay, everything is quantized. Charge, we already discussed, is quantized, right? The smallest charge doesn't go below the charge of an electron. Electron is the smallest charge, so it is charge. Charge is quantized, right? We already discussed that. Now, also energy in certain ways is quantized, and then inside that atom there are what are called energy shells. All this was discovered, and we will go into both the discovery process as well as the experiments they used. We already discussed one of the experiments when we discussed light. But in the context of class 11, we discussed the Young's double slit experiment, which explained how light is actually a wave. And how in the when you look at the slit, light seems to move different paths during when you introduce these two double slit, right? So we introduce the wave nature of light, right? And then we introduce the particle nature of electrons and the wave nature of both. Eventually there was what is called the wave particle duality. Okay, so we will discuss all that as well. Wave particle duality. Then we will introduce the wave nature of things. What Heisenberg said and what Schrodinger said, and then what Einstein said. And how they all came together to then agree on a intellectual peace. And and then they went about further exploring things more. In science there is no war. In science there is only objectivity. Okay, different people can have different theories, but then objectivity decides which is right and which is wrong. Okay, so keep that in mind also. It's worth learning. Okay, the other thing that, as I said, we will be introducing deals with electronic devices, right? Let me also bring up that set of slides. We will be going over this insulators, conductors, etc. Okay, and again, and then we will introduce this new thing called the semiconductors. Okay, so and so while we are there, let me introduce to you our two apps. Okay, the first app that we provide is the Sushruta for NEET students. So you go to play.google.com and you type in com.JnanaMarga.Sushruta and you download the app. Once you type com.JnanaMarga.Sushruta and download the app, then you will be able to install it on an Android compatible cell phone or an Android compatible tablet. Similarly, for the JEE students, we also have Ramanujan, com.JnanaMarga.Ramanujan. Okay. So you can download either of the apps and then you can use it to study. So now you have insulators, conductors, semiconductors, as which we will be discussing as part of our electronic devices study. Okay, so so that is what is to come with respect to physics. Okay, now modern physics is covered in the second book of Concepts of Physics by Professor H.C. Verma. Okay, Concepts of Physics by H.C. Verma. Now, if you buy a tablet solution, we provide Concepts of Physics on the tablet in electronic form. And while you're reading your NCERT textbook, you can then also go to Kindle and look at the particular chapter we are pointing you to. Okay, so you read the chapter in H.C. Verma, you solve the problems in H.C. Verma, you look at the examples in H.C. Verma, and you also look at the IIT PAL videos corresponding to modern physics, and then you get a very good and excellent conception. On top of that, you also have my lectures. So you have a lot of material to go by, and now there is also assessment in the two apps. So students gain a lot by taking advantage of all these things. Okay, so the student who is diligent, who takes advantage of the program, these are very affordable programs, they will gain. And there is no point waiting till March for a May exam and then say, I studied for 1 month with your app and nothing happened. You will still gain. You will study for a couple of months, but you want a full success, start when you're in class 11 with that. So that is the most important idea that I want to convey here. Okay, so having conveyed that, let's now get going with atoms. Okay, so okay, so in the late part of the 19th century and the early part of the 20th century, there were many models with respect to the atom. People had already discovered by then, Mendeleev had made the periodic table, and they knew that elements consisted of this thing they call the atom. Okay, so a pure gold consists of entirely atoms of gold. Okay, pure oxygen consists entirely of atoms of oxygen, right? So, or in oxygen's case, molecules of oxygen, right? But underlying this, there is the atom. Okay, now what goes inside the atom and what are these things that facilitate electricity called electrons, right? And the discovery of both of these, all this became a important topic of science, towards the end of the 19th century. Late 19th century, they spent a lot of time trying to understand the atom, and they came away with fantastic results. Now, the first person to propose a model for the atom was Thomson. Okay, and he did several. Thomson's experiments are very famous. They were the first experiments pioneering work in the atom. Okay, he said every atom is uniformly charged sphere of radius of the order of 10 to the power of minus 10. Okay, 10 to the power of minus 10 is what? 1/10 of a nanometer. 10 to the power of minus 9 is a nanometer, right? So 1/10 of a nanometer is this thing called an angstrom. A, put A and put one circle on top. Okay, it's an angstrom. 10 to the power of minus 10 is an angstrom. So he said it's roughly the size of it is about an angstrom, in which the entire mass is uniformly distributed and negatively charged electrons are embedded in this. Okay, so the atom as a whole is neutral. There's no charge in an atom. It has electrons and these positively charged things. Okay, and then it's all inside there. It's one blob. Okay, now there were many limitations. It could not explain the origin of spectral series of hydrogen and other atoms. It could not explain large angle scattering of alpha particles, and we will discuss alpha particles very soon. Okay, and this is what is called the plum pudding model. So this looks like a plum pudding, right? So there is plum pudding. In a plum pudding, there are all these things inside a pudding. This is the pudding, and there are many plums. Okay, now plum pudding model had issues. So the next person who came up with the model was this Englishman called Rutherford. I think Thomson also probably Englishman. Okay? Rutherford's model, right, on the other hand, looked to the stars and he said, let's look at the planetary model. There's the sun at the center, and there are all these planets. Okay, so he then said that the electrons are like these planets which kind of go over the protons which are in the nucleus. So he said there is a dynamic equilibrium, just like in the case of the sun and the planets, and these the sun is big and the planets are small, but then the space occupied is much larger, right? So he gave this planetary model as the solution to how a atom is. Okay, now, he said the on the basis of the experiments that were actually done by Thomson, or originated by Thomson and then followed on by Rutherford, what Rutherford said is that the entire positive charge and almost the entire mass of the atom is concentrated at its center in a tiny region of the order of 10 to the power of minus 15. Remember, the size of the atom, they said, is a 1 angstrom, 10 to the power minus 10, right? So he said that there is a highly charged nucleus, 10 to the power of minus 15. Okay. And so what is the difference between 10 to the power of minus 15 and 10 to the power of minus 10? It's huge. It is 10 to the power of 5. So what is 10 to the power of 5? Okay. So now, if I had a ball of, maybe 10 centimeters radius. Okay. So now if I had a ball of 10 centimeters radius, right, this would be 1,000 meters. Okay. So 10 to the power of 6, because it's 5 times bigger, right? So 10 centimeters, 10 to the power of 6, 1,000,000 centimeters in size. What is a million centimeters? It's about, several, almost 1,000 meters. So that is the magnitude between of size difference between the nucleus and the uh, the atom itself. So there is free space in between. Okay, so much empty space in between the nucleus and these electrons revolving around. The negatively charged electrons revolve around this nucleus. It is a tight mass at the center. The total positive charge nucleus of the nucleus is equal to the total negative charge of the electron. That's how you have overall neutrality. They had to explain that overall neutrality, right? And so, so that was the Rutherford model, and Rutherford almost got it right, but then not. There is a lot more than that. Okay, so now let us look at the Thomson model and the Rutherford model. Had Thomson's model been correct, all the alpha particles. So this was the Michelson-Morley experiment, I think, or there's some experiment, Geiger-Marsden experiment, which where what they did was they had a vacuum. In a vacuum, they had an alpha particle source, and they passed that alpha particle source through a gold foil. Okay, and so pure gold foil, and what they found was that the gold foil, if the Thomson model was there, then you will have it flow all the way through. But then in the case of the gold foil, they found that there was a lot more scattering of the alpha particles. Okay, and so Geiger and Marsden, they found that a small fraction of the alpha particles experienced significant deflection. You can see this picture, right? They found some of the particles would just fly off. They'll go be pushed like that, pushed like that, pushed like that. Okay, really great strong deflections. Why was that? That was because, and if you had this kind of plum pudding wouldn't cut it. Okay, it wouldn't be able to like kind of go through the plum pudding and reach everything. All of them would reach, go through the plum pudding and reach the other side, right? If there was a uniform mush, right? This kind of heavy deflection is only possible through the Rutherford model. concentration. Okay, so if there is concentration, then deflect like that, deflect like that, deflect like that. Okay, so this deflection was what Giger and Marston observed, right? Therefore, they came up with this idea that the total positive charge of the nucleus is equal to the total negative charge of the electron. The atom as a whole is neutral. The centripetal force required by electron for revolution is provided by the electrostatic force of attraction between the electrons and the nucleus. Okay, so why do planets go around the sun? There's a gravitational force, right? It's a weak force. Now this nucleus is right here. The electrons are so far. So now if we do the calculation, right? What keeps these electrons in this space is because of the electrostatic force. It's a much stronger force, and that is allows for these electrons to be so far away from the nucleus. Okay? Therefore, this also explains this kind of heavy duty. When an alpha particle is pushed in at a gold thin foil, then how these alpha particles get scattered. Now, alpha particle is like a helium nucleus. Okay, so now the distance of closest approach is 1 by 4 pi epsilon naught 2 z e square by ek. Ek is the kinetic energy of the particle, right? So now E naught 1 by 4 pi epsilon naught E square E1 E2 by 2 z e by r. That is the kinetic energy, right? So you need that kind of kinetic energy, right, to completely repel these alpha particles. Okay, therefore this is the kinetic energy of a that is there. Okay, and therefore the perpendicular distance of the velocity vector of an alpha particle from the central line of the nucleus, that is the impact parameter. When the particle is far away from the nucleus, is called the impact parameter. So it comes wide. What causes that it to bend like that and go? That is what they were looking at. Okay, so so what is the angle, right? So when where z is the atomic number. So why do they introduce z there? Because inside the nucleus there is the protons. There are z protons. If a nucleus has a atomic number of z, so hydrogen has atomic number 1, helium atomic number 2, like that. So if you had gold, it has a corresponding atomic number, I don't know, 57, whatever it is, so it has that many protons in the nucleus. So, and each proton has so the nucleus has a net charge of z times e, and a individual particle will have a corresponding e, right? So therefore you end up with 1 by 4 pi epsilon naught z e square by r, and r is b by cot theta by 2. Okay, and therefore he introduced, using the simple mathematics, he introduced this the b, okay, the corresponding b. Okay, so that is what led to the electron being deflected. Okay, so and the Rutherfords, he then brought in this scattering formula, the number of particles that will get scattered, right, versus the total number of particles. He derived a formula for that. Okay, so you throw a bunch of particles, some will go through, right, but that small percentage, the number of charged particles that will get deflected, he did a calculation and he came up with a number for that, and that was what was very creditable by with respect to Rutherford, and he therefore came up with the nuclear theory with respect to the planetary theory. Now there were still issues, and The first issue was about the stability of the atom according to electromagnetic theory should emit energy in the form of electromagnetic waves during its orbital motion. Therefore, radius of orbit of electrons will decrease gradually and it will ultimately go into the nucleus. So if there is any perturbation when an atom is rotating, it will then spiral back into the nucleus. The electrons spiral back into the nucleus, and that never happens. Atoms are extremely stable, at least barring the uranium and these radioactive materials. Rest of the atoms, they stay the same forever. You keep a box of oxygen, it stays a box of oxygen, doesn't become suddenly helium or something else. So that's the reason why it won't fall into the nucleus and then lead to the charge destruction. Always this many electrons orbiting, and that what causes that stability of the atom. And so that was not provable by Rutherford. The second thing, the line spectrum of the Rutherford could not explain the atomic line spectrum. You have the hydrogen spectrum, helium spectrum, etc., which produce these lines. Those hydrogen spectrum, helium spectrum, etc., were not being explained by the Rutherford model. Okay, so those were the two initial models that were discovered. Okay, so there was the Thomson model, and then there was the Rutherford model. Let me take a moment to tell you which chapters in H.C. Verma to read for this. Okay, the chapter in H.C. Verma to read for this is chapter 43. Okay, and so the difficulties, it has a section called the difficulties with the Rutherford model. So you read that chapter, then we will move on to the next model which became successful. Okay, that model is called the Bohr model, and it was founded by this person called Niels Bohr. Okay, so let me then introduce the Bohr model. This part of atomic theory is actually very, very interesting, and you have to learn it not just for your physics, but also when you study chemistry. Particularly, I will show you a textbook to read. The Atoms First textbook for chemistry, which is freely available, is a very good book, and I will show you that book as well. Okay. So now, let's continue. Okay. So, de Broglie, right? He came up with this, what is called the wave particle duality. Okay, and so wave particle duality, right? It is there in chapter 42 of your textbook of H.C. Verma. Okay, so wave particle duality. We will again look at it when we look at also in the next class when we look at when we also look at photoelectric effect. Okay, so now wave particle duality was first explained by this person called Louis Victor de Broglie. Okay, and he said there is H, which is the Planck's constant, H divided by P, which is the momentum of the electron. H divided by P will give you the lambda of the electron. Okay? And therefore, his explanation was that an electron also, which many people thought was just a particle, was also a wave. Okay? And therefore, wave particle duality, H by P equals lambda. Okay, so wave particle duality little bit complicated things a little more, but then it eventually led to the discovery, to Niels Bohr's discovery of the atomic model. Okay, now the energy, right, is given by h times mu. The energy associated with a wave is given by h times mu, where h is the Planck's constant. Okay, E is equal to h mu. Okay, so for light, right? Similarly, now, and C is equal to mu lambda, right? That you already know. We already talked about it just now, right? C equals mu lambda, right? And E is equal to h mu. Therefore, E is also equal to hc over lambda. Now, in the case of the electron, right, post this de Broglie, right, he said that h by p, right, h by p is also lambda. What is p? P is the mass times the velocity of the electron. Okay, so in the case of and then, so as a result, they were able to discover this idea of wave particle duality. Okay, so now E is also equal to p square by 2m. P is mv, right? So p square by 2m is what? Half mv square, right? So E is what? The kinetic energy. Kinetic energy is half mv square, right? So half mv square is also p square by 2m. Okay, and therefore, when you plug that in, you have the velocity of the wave is equal to mu lambda E by h times h by p. Okay, therefore, uh, so that is the basic set of details that you need to learn. Okay, now Einstein's relativity is changed, the resultant ideas associated with this, E equals mc square by square root of 1 minus v square by c square, right? Basically, E is equal to mc square, right? So now, um, um, so the important ideas around this will help you, calculate the associated uh, particle versus wave nature of each of the underlying particles that we discuss, including the waves that we discuss in the context of light, and the electron as also a wave. Okay, so this what essentially happened was they found that as a result, they were getting a different speed from one and a different speed from the other, and therefore, people started to then try to integrate these two ideas. Okay, and therefore there was the people in chemistry like Mendeleev, and who came up with a periodic table. Then there was Dalton, who also had an atomic theory. And then there were all these Priestley and all these people doing experiments with radiations. Okay, the main problem, as we discussed last time with the Thomson theory, was that the plum pudding theory didn't hold muster when when they attempted to bombard the gold foil experiment with alpha particles, right? Because some of the alpha particles were getting scattered, right? So we already discussed that. Now, Rutherford therefore overturned Thomson's model in 1911 with his gold foil experiment. So that said, so then he said there is another model, and for a long time that was the model that stayed almost 20 years, which was the Rutherford model. But then people poked a lot of holes at the Rutherford model, and but what Rutherford should be credited for is that he designed an experiment to understand what was the unseen world of atomic structure, and he introduced these alpha particles which are emitted by these radioactive elements, and then he used probes to look at what all they are doing. Okay, so that this gold foil experiment was a big deal because of that, right? He looked at the underlying world. The world of the atom is a mystery, and even today, because you can't see it. So at the very atomic level, except now, of course, you have these newer electron microscopes, etc. Therefore, he came up with this Rutherford model, and where he discussed that he came up with the planetary system, and then he said the centripetal force that holds the electron in place, it comes from electrostatics. Okay, so that's how they but the problem was that the nuclei were stable and there were these emission spectrums which could not be explained. Okay, but then what he could explain was this, how many, if you had a thin foil, how many of these particles would be deflected and how many would go straight through. Okay, so that was the details of what he did, and it's always a very respected person who understood atomic atomic models. Okay? So now, in the case of the electron, though, right? The most electrons also pass through, right, when they push electrons against the foil, but there were a lot more that were getting scattered. Okay, and so this led them. So when they used gold, right, what was the cross section? How many were getting scattered when they used gold? When they used boron, gold was a lot. Okay, the number that was getting scattered declined for phosphorus, and it declined even further. The recoil angles, were much smaller for boron. They were higher for phosphorus. They're even higher for gold. What that meant is that this concentration, there are many more protons there, and they would kick you off much faster and much further. The angle of recoil was much further. The worst angle of recoil is when you go head on into the nucleus, then it deflects significantly further. Okay, so that was the main thing that Rutherford was able to show. And that's why you have these recoil angles in this picture, right? And so that is the analysis of Rutherford's experiment. Okay, so the ME by M alpha, right? So when you put an alpha particle, you got a certain recoil. When you put an electron, you got a different recoil, right? So based on that, he was able to get the ratio of the weight of the electron to the alpha particle. That was ended up being 1 by 8,000, and that was the difference in the mass of the alpha particle to the electron. And so the proton, right? He basically said that other electrons don't repel these electrons. What repels these electrons is due to the charge. Okay, and so this charge is basically the positive charge, and so the radius of the atom was like a pin compared to a football field. That's the most common ratio that they use. Okay, and so then they said that there is a central nucleus, Z equals 87, right? Atomic number of gold, and it's a spherically symmetric distribution, and correspondingly, you have a nucleus of a certain size. They were able to determine the nuclear size, or was 10 to the power of minus 14 meters. Okay, so having determined the nuclear size, they then we can then move on to then introduce the next set of ideas in with respect to atomic physics, which is, of course, we're all slowly heading towards the Bohr model. But before we go to the Bohr model, we first have to understand a little bit more about the Rutherford's scattering experiment. So let me a little bit explain his scattering experiment so that you get an idea of what went wrong. Okay. So first, let's look at the apparatus of Rutherford scattering experiment. Okay. So he used a isotope of bismuth. You know, so what is an isotope of bismuth? Okay, an isotope of bismuth is something is said to be bismuth if it has a atomic number of 83. Okay, but its other number 214 is can change. Different isotopes will have different uh, 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 you know atomic masses. Okay, so now he using bismuth, he he generated alpha particles and he made them move with a great energy using electromagnetics. Okay, so now once he generated these alpha particles and then he created this lead screen with a slit in the middle so that they would be channeled into a certain in a certain direction. He then used allowed them to pass through that hole in the lead screen and then go and hit a thin gold foil whose thickness he had very meticulously and carefully made to be 2.1 into 10 to the power minus 7. Okay, if it was any thicker, it was a lot thicker. Let's say you put a gold bar there, nothing will show up. Everything will get absorbed by the gold bar. Okay, so he had become cut very thin, very precise, 2.1 into 10 to the power minus 7 meters, and then he bombarded that gold foil with these alpha particles. Then he placed a fluorescence screen on the other side, and therefore he found that a certain number went through, certain number was deflected, and then that ratio of the number that was deflected to the number that went through, formed, that ratio was that n I versus n theta, what saw maximum deflection versus what went through. That ratio was what formed the the discovery of both the radius of the nucleus as well as finding the it was that which set up the discovery. Okay. Now, scattering in the Rutherford experiment takes place because the positive charge is stationary and it is centered in a concentrated central nucleus. The field produced by these charge distribution is 1 by r square, as you all know, right? And therefore, things that go directly towards the nucleus, right, which occupy that small space, they had a probabilistic value for if when it would go and hit the nucleus, and when it would like fly here and fly there, right? When it would fly here and fly there, it would go sometimes through the thin foil and then go all the way there. Okay, now, but then there were certain things that would come and they would deflect and deflect big, and so that is scattering is characterized by that impact parameter where it would approach, close, and then get deflected. Okay, so because as you know, like charges repel, right? The protons in the nucleus had the same charge as the alpha particle. So when the alpha particle came, it would boomerang, like a boomerang. It would return. It would almost turn around and come. Okay, so scattering is characterized by that impact parameter. And therefore, if your kinetic energy is larger than threshold energy, it would penetrate the charge distribution. Thus, as R tends to 0, energy will be infinite high. Now, scattered particles follows a hyperbolic path. Okay, this hyperbolic path, this makes an angle theta. Therefore, it kind of goes in a different direction, and based on how closeness of the approach to the nucleus, it would then correspondingly deflect. Now, he then tried the same experiment first with gold, then he tried it with phosphorus, then he tried it with boron. He found that these recoil angles with gold were the highest, and that corresponded to the 87 atomic number of gold, lower with phosphorus, and even lower with boron, because boron is H HeLi BeB, 5, right? Boron is 5. And then phosphorus is 9, I think. I don't know. So whatever phosphorus number, it's not high either, but it's more than boron. Therefore, correspondingly, he was able to show what that recoil angle was. It was much lower for boron, much higher for uh, 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 gold. Large portion of alpha particles pass through the sheet without getting deflected, because that's how concentrated the nucleus is. The positive charge is not uniformly distributed and is concentrated in a small part of the atom. Okay? Therefore, he came up with this nuclear theory. The atom is electrically neutral. An electrostatic force holds the nucleus and the electrons. The electrons are in orbits, but then he said that they are in fixed orbits. And but that was the issue that they faced. The issue was the stability of the atom and explaining these discrete spectral radiation. Okay. Now, the spectral radiation was shown to be due to the change in the quanta. So when an electron goes from one shell to another, you have these spectral radiations. Okay, so we will discuss that. Otherwise you should see if it was going in random direction, you get random radiation. They weren't seeing that random direction. They were seeing fixed spectral radiations, and to explain that constant, was where they needed to understand this better. So, but the stability issue was like this. The electrons, the EM radiations emitted by the electrons, right? So if you emit a radiation, you lose energy, and when you lose energy, should then carry and move and go into the nucleus. But that was not happening. Okay, so what they said was there must be a lowest state at which the electron is stable, and from there it doesn't go into the nucleus. So it sits in orbits, and there is a lowest orbit beyond which it does not emit any energy. So it will come from the higher orbit, lower orbit, will emit energy, but when it goes to that lowest orbit, after that it will not emit any energy. There must be a lower state that the electron stays stable. So now it also did not explain the discrete nature of these spectral lines: Balmer lines, Lyman series of lines, Ritz-Passon lines, Fund series of lines. There were all these spectral lines that formed the Vibgyor spectrum, right? And they formed distinct lines, and so these spectral lines were not being explained, and they felt that these spectral lines, which are caused when the electron moves from one orbit to another, and the Rutherford model did not explain it, being a more model which deals with continuums, right? In a continuum, you will not see this kind of quantization lines, hc over lambda, right? So why do you get this particular energy change? So why does it go from one higher energy to a lower higher energy, to a lower level energy, right? So, and when it goes from higher energy to lower energy, it emits only this particular frequency, this particular wavelength light, right? What is that hc over lambda? Why is that lambda fixed, right? Hc over lambda, the change in energy leads is so that explanation, they needed to introduce this other idea called quantization, and quantum theory into the atom, into the atomic model, and so with that, I am going to close today's lecture because we run out of time, and we will meet again next class, which is next Sunday morning. Okay, so until then, let's hope for an India victory, right? Let's hope for an India victory tomorrow, and let's hope that we meet again and we're all cheerful and laughing as we go forward, following an India victory. So, but then in the meanwhile, please download our app and start working with it. The assessment platform is there. Solve questions, read the chapter and solve questions. I cannot emphasize this anymore. Without that, you are not going to do as well as you would if you really studied. You must also study, you must also, burn the midnight oil and solve problems. And then you must come back with questions. That's how these battles are won. These are not easy battles. All right, I'll see you next week. Thank you.